Welcome everyone. My name is Professor Aziz Arbai, and today I will present a new methodology for efficient attitude control and state prediction for satellites via direct 3x3 matrix power calculation. Let's start with the core objective. The main challenge in modern CubeSats is that real-time attitude control systems face severe power constraints. Traditional predictive model rely on iterative matrix operation with an theta n complexity, which are highly prone to numerical drives. Our solution is a robust, closed-form algebraic methodology based on the Cayley-Hamilton framework. This computes the nth power of 3 times 3 transition matrix directly in θ1 constant time. The K results is reduction of floating point operation by over 99%, completely eliminating matrix warping. CubeSats have democratized access to space, but they operate with stringent resource limitation, such as low power microprocessor and restricted battery capacity. Despite these, modern missions demand high frequency updates for precision tasks like laser communication and autonomous formation flying. The primary computational bottleneck in this system is orientation control, which requires the continuous integration of rotation matrices within the special orthogonal group SO3. Traditional iterative methods for computing matrix power drain flight battery due to their theta n complexity. Furthermore, commutative rounding error creates matrix warping, which destroys the orthogonality of the matrix and requires costly normalization steps. Our scientific contribution bypass these traditional numerical loops entirely through exact algebraic reduction. We successfully reduce transcendental matrix function to finite second degree polynomials. Importantly, we achieve this without needing traditional spectral decomposition or diagonalization. To model the satellite dynamics, we begin with the rigid body-Euler equation, where G represents the 3 times 3 inertia tensor. By linearizing this system around finite pointing equilibrium points for digital onboard processing, we obtain our discrete time transition model mapping to state xk to xk plus 1. Here is the fundamental methodology. By the Cayley-Hamilton theorem, any 3 by 3 matrix satisfies its own characteristic equation. Consequently, any higher power of our discrete matrix collapses into a quadratic polynomial. This marks a paradigm shift from theta n to θ1 constant time complexity. The computational cost is now entirely independent of the prediction horizon n. To find the scalar coefficient a n, b n, c n, we solve a linear van der Monde system using the eigenvalue of the matrix. This unique solution is highly efficient because it bypasses the need to compute explicit eigenvector. Unlike traditional spectral decomposition, our algebraic reduction is universally robust. It seamlessly handles complex eigenvalue by mapping coefficient directly into the real domain, saving onboard complex arithmetic. It is also completely robust when dealing with multiple eigenvalue or non-diagonalizable matrices where standard routiness typically fail. Applying this mathematics to model predictive control brings a major computational leap because the power of the transition matrix are evaluated independently. State prediction are parallelizable. This allows for much deeper look-ahead horizon without adding processing stress to low-power processor. We benchmarked this method over a 1000-step prediction horizon. The traditional iteration method requires roughly 27,000 operations and suffer from significant numerical drive. In contrast, our proposed method requires only about 45 constant operations and yields zero drives. This represents a 99% reduction in computational effort. In practical terms, for cube sets, power is the absolute limiting factor. Minimizing clock cycles prevents onboard the processor overheating and directly translates to prolonged battery autonomy. These ultimately empower satellites to execute complex maneuvers completely decoupled from ground station assistance. To summarize, we established an analytical framework that substitutes costly theta n numerically loops with a deterministic exact theta n1 a quadratic polynomial. Matrix warping is eradicated and computational velocity is enhanced. Our future horizon include extending this framework to higher order nonlinear structure and implementing it in decentralized global satellite swarm synchronization. The following slides contain the reference that supports our work. Thank you very much for your attention. I would be happy to answer any question.